Hello everyone, I'm J Wildberger, and it's a special pleasure for me today to introduce what I think will be an important new series on the interface between mathematics and physics, having to do with the fundamental nature of symmetry and how we address that in the mathematical sciences. So I'm going to be proposing a somewhat new paradigm for symmetry in mathematics and physics, and I hope this will be particularly interesting to physicists. So I would like to introduce these two notions that currently we're dealing with symmetry from a transformational point of view. So we could call this transformation symmetry. This is the symmetry that's found in most texts and most approaches to physics, which is broadly based on group theory. Okay, so the idea is that we're studying some object or some situation, some dynamical system, whatever, and we're interested in the transformations of that system that preserve some quantity or quantities of interest. And typically, if we set things up the right way, these transformations form a group. So the theory of groups plays the big role. Now, these groups that appear can be finite groups, they can be infinite but discrete groups, but they can also be continuous groups or Lie groups. So there's a wide variety of different kinds of group theory that fit here. So this is the standard approach to symmetry, universally accepted. But I'm proposing that there might be good reason to consider another kind or approach to symmetry, which I'm going to call diffusion symmetry. Here are some of the features that distinguish it from transformation symmetry. And in terms of the motivation, well, I guess standard group theory, its motivation is based on the motion of rigid bodies. We have some object in space and we can rotate it, or we can translate it, or maybe we can reflect it, or do some other things to it. And these are the building blocks upon which standard group theory is based. Here, we're going to be thinking, I'm going to try to encourage you to think about diffusion of a gas as being a sort of a principal model for this new kind of approach to symmetry. So to explain what I mean here, let me do a bit of a thought experiment where we imagine we're in a room and we have a small balloon of some gas. And let's assume that the room otherwise doesn't have anything, so we're essentially in a vacuum. And we have a little bit of a balloon of gas somewhere in the middle here. And at some point we pop the balloon, we release the gas very suddenly. Okay, so the balloon is gone. So the walls that were constraining the motion of all these molecules of the gas, molecular motion of the gas molecules bumping into each other, bumping into the walls of the balloon. The walls are suddenly gone, so now these particles can fly off in different directions throughout the room. Then what do we expect to have happening? Well, after a very short amount of time, we expect that the gas will have sort of expanded by a certain amount, right? The particles, a lot of particles will just head out in various directions. So it'll be sort of like a spherical wave front that emerges from the initial position of the balloon. There'll still be some particles that are sort of bouncing around off each other inside and so on, but they will thin out. And as we watch this thing, this spherical wavefront will emerge and head towards the walls. And once it gets to a wall, well, it'll sort of bounce off the wall, okay? And there will be dispersion, and so everything is weakening as we go. But roughly speaking, for example, at this stage here, the majority of the spherical wavefront is still expanding, but maybe the top has reached the ceiling. Maybe the initial position of the balloon was closer to the ceiling, and so this has already reached the top and it's now coming back down. And then after some time, if we watch this for a little while longer, of course the gas is eventually going to become more and more uniform. But before it does that, it will still have some structure that's determined by where the initial balloon was, but also is determined by the shape or the symmetry of the room. So for example, at this later stage here, maybe the spherical wavefront has largely sort of come back towards the center, and its shape roughly will be somehow representative of the shape of the room. It will contain some information about the shape of the room. So that the diffusion of this gas, if we could sort of watch this gas diffuse, and we say don't have an understanding of the actual shape of the room, maybe we can get some understanding of the shape of the room by watching the diffusion of this gas. So I believe that the general orientation that I'm going to be talking about to you today was probably initiated at some level by George Frobenius in his landmark paper of 1896 on group characters, where he's pioneering the study of the characters of non-commutative groups and ultimately then the connections with representation theory. So I think the seeds of the idea are already in that paper, but they have been rediscovered and redeveloped and reintroduced in a wide variety of contexts, and often in very different fashions and with very different motivations and orientations. So let me cover some of the ones that at least I'm familiar with. I'm sure that there are more that I'm not aware of. So we can talk about Kawada in 1942 introduced the idea of a C algebra. This is very close to this general idea. Leviton in 1962 studied what he called generalized translation operators. And Brouwer, in 1968, studied pseudogroups. So all of these theories have something to do with this general direction that I'm going to try to explain to you. But then there are all manner of other concepts which are also variants or special cases or something pretty closely associated with this, including hypercomplex systems, Bose-Mesner algebras, and association schemes coming from combinatorics, Hecke algebras coming from Lie group and algebra representations, paragroups coming from von Neumann algebras and 2-1 factors, super selection sectors, some physics, centralizer algebras, group theory, Rocca-Wigner algebras, also some physics, fusion rules, tensor products of representations, table algebras, group theory, hypergroups. Okay, these in particular are the ones that I sort of grew up learning about from the papers of Dunkl, Jewett, and Spector. Okay, so when I started this understanding these things, it was all in the context of hypergroups, and eventually, gradually, I realized that there were all these other things floating around that were hypergroup-like in nature. So I'm still kind of oriented towards the hypergroup structure, but I also have quite an interest in fusion rules and association schemes and group characters because I have a Lie group sort of background. But that figures very prominently in my understanding of things. Okay, and now there's quite a few more, but especially I'd like to point out in modern times there are things called fusion categories. So this is part of category theory, where people look at extending this fusion rule story to more general settings. So this is a big, a big list of things, and it's hard to get one's head around even a sizable fraction of these things. But I hope that during the course of these lectures I'll be able to touch base with quite a few of these things, and you'll start to see that there really is some kind of unifying thread here, and that I think there's an underlying unity of point of view that is possible, and that once physicists especially become more aware of this, not just some particular aspects, but the general thrust, I think it will be very empowering and will open up new doors for an understanding of modern physics, especially having to do with the standard model and perhaps string theory and things like that. So I'm now going to try to indicate roughly the direction of what we're going to be talking about through an example. And in fact, in general, I'm going to try to emphasize examples because a lot of this material is potentially quite advanced, and I don't want to get bogged down into having to redo Lie theory or affine Lie algebras or von Neumann algebras or whatever. So I want to try to stick to examples and illustrate things via examples. And I'm especially thinking about physicists who might be watching who maybe are not that strong mathematically, although some physicists are very strong mathematically. But I want to illustrate things sort of concretely so that you can get your hands dirty. And maybe it's useful for me to say a little bit about my motivation. So a few words just about me, if you haven't watched many of my videos before. So I'm a mathematician. I got a PhD at Yale University, and I taught for some years at Stanford and at the University of Toronto. And for the last 30 years, I've been teaching at the University of New South Wales in Sydney. And I've just recently retired about half a year ago. And I have lots of YouTube videos on various aspects of mathematics. And I have a second channel called Wild Egg Maths. And I hope some of you will consider becoming a member of that, because I'm there initiating a series of explorations in various interesting topics of mathematics. And one of them has to do with exceptional structures in mathematics and physics. Things like E8 or the 27 lines on a cubic or the octonions and things like this. And but I'm doing it through dynamics on graphs. And in the course of thinking about that, I realized that eventually I'm going to have to touch base with this topic of hypergroup-like objects, this diffusion approach to symmetry. And it's just such a big topic that it really deserves kind of a separate discussion. And I think it's really potentially useful for physicists. So that's my motivation. Okay, so what we're going to do here now for the rest of the lecture is talk about mostly one example where I can illustrate some of the ideas of what's going on. And I'm going to leave it to you to maybe do some checking and fill in some details. And some of the theoretical aspects, don't worry about it too much. I just want you to see what's going on. So here's a graph. Okay, it has how many vertices? I should say that these vertices here on the edges, the ones with the open circles, they're all meant to be the same. Okay, so this vertex, all of these 5 here are identified. So I could have avoided that by, say, choosing one of them and wrapping the others around to that. But that would have then broken the evident symmetry that you see with this graph. This graph has a 5-fold symmetry around the center. You can kind of see that rotational symmetry by 1/5 of a turn. And it's got how many vertices? Well, there's one there, and there's a ring of 5, and then there's another ring of 5, and then there's this one outside one. So a total of 12 vertices. And so let's ask 2 questions. One is a rather general one. One is a rather specific one. So the rather general one is, how symmetric is this graph? Okay, so this is a very general question. So we're interested in symmetry. We can see that there's some symmetry here. How do we describe the amount of symmetry or the nature of the symmetry of this graph? Okay, that's one question. And a more specific question is concerning a sort of a random walk on the vertices. So if you start, say, at this central point A, and you make a random walk, that is, you walk from one vertex to another. And at each stage, well, let's say at this stage here, you've got 5 choices. So you choose one of your neighbors at random. Okay, and then you just walk there, and you keep doing that. So what's the probability of a random walk of, say, of n steps, returning to the central or starting point or vertex? And to be specific, let's say for example, if n is equal to 11. Okay, so a walk of 11. So I start here and I go 1, 2, 3. That's the same as that. So the 4th one could be there. 4, 5, 6, 7, 8, 9, 10, 11. Okay, I've come back to the starting point. What's the chance, what's the probability that a random such walk with 11 steps gets back to the starting point? Okay, so we want to analyze this graph rather generally, and we want to have enough information about it so that we can address this rather complicated question. So this is not an easy question. Given a random graph, especially if it's bigger, this is going to be really hard to calculate, I think. But somebody who is versed with some group theory can appreciate that knowing the symmetries of this object is going to help us in tackling this random walk question. So let's ask ourselves, what kind of symmetry does this have? And I'm going to ask it from a diffusion point of view. Okay, so we're not going to ask what are the transformations or what are the automorphisms of this graph. Okay, that would be a group theory point of view. I'm going to rather think about local information. So a first thing to ask is how much do the various vertices look like each other? Okay? And a first way of doing that is to ask about the degrees of each vertex. So in other words, the number of edges that emanate from each vertex. So let's count the degrees of the vertices. This one here obviously has degree 5. There's 5 coming out. This one here has degree 5. And there's sort of a symmetry, so once I've calculated that one there, it's the same is true for that ring of 5 there. What about this one here, which is sort of 2 steps away from our central thing? Well, it has how many neighbors? 1, 2, 3, 4, 5. It also has 5 neighbors, and that's going to be true of all these other ones. And finally, this outside one, which is sort of a step 3 from the center, how many neighbors does it have? Well, each one of these outside ones here is a neighbor of the far outside one. So it also has 5 neighbors. So this graph has the property that the degrees of all the vertices are the same. Okay? So that's sort of naive, sort of initial step at thinking that there's some symmetry here. But basically what we're doing is we're looking at the graph from any one vertex, but not looking very far. We're just looking sort of one step out and doing some calculation just in that little ring around where we are, namely counting degrees, okay, and then comparing that. So we can think about upping that or becoming a little bit more sophisticated about that and looking not just at the directly neighboring things, but maybe the things which are, 2 steps removed or 3 steps removed from a given vertex. All right, so to make some further developments, let's give our vertices names. So let's call this one A, this one's B, C, D, E, and F. Here's G, H, I, J, K, and this outside one is L. Okay, and now let's define for a vertex X, no matter where it is, C of X will be the multiset of neighbors of X. So I'm going to use a data structure called a multiset or an M set, which is dear to my heart. Okay, an M set is like a set. It's unordered, but repetitions are allowed. Okay, and my standard notation for that is to use square brackets. That's telling us that repetitions are allowed. And I'm not going to put commas. I'm just going to separate the things with spaces. That's telling us that the order of things doesn't matter. So for example, C of A is this vertex here, is the multiset of neighbors, and that's just the multiset consisting of B, C, D, E, and F. So now I want to calculate C of A. Okay? So what's inside here is a multiset, and I want to apply the C operator to it. So what does that mean? Well, typically when you're working with multisets, if you perform an operation, you want to just perform that operation on each of the elements and put them all together. So what I mean here, it's like the multiset, which is like C of, in this case, C of B, plus C of C, plus C of D, plus C of E, plus C of F. Okay, where the plus means the addition of multisets. So if you have a multiset here and a multiset here, addition just means that you dump them all together, okay? It's not a union. With a union, you'd have to sort through and remove duplicates, etc. Now here, you're just sort of dumping them together. Okay, so let's see if we can calculate this. So what is C of B? Well, I'm going to make a big multiset, okay? So what's C of B? What are the neighbors of B? So I'm going to just run through them. So there's G, there's H, there's C, there's A, and there's F. Okay, so those are the neighbors of B. And now the neighbors of C. I'll go this way. So there's H, there's I, there's D, there's A, and there's B. Okay, I've gone around that. And now the neighbors we're going to go over here. The neighbors of D are stay here, starting with I, and then J, and then E, and then A, and then C. And the neighbors of E are, let's say, J, K, F, A, and D. And finally, the neighbors of F are, say, G, B, A, E, and K. Okay, notice that L doesn't appear because L is a little bit too far away. Okay, how can we think about this? Well, let's have a look. How many G's do we have altogether? Well, there's 2 G's. Is that right? Yeah, there's 2 G's. G is this one here. How about H's? Well, there's going to be 2 H's. Also, there's an H there, and there's an H here. Okay, that's kind of obvious because of this rotational symmetry that we've already observed. Everything is rotationally symmetry. So if we get G 2 times, we're also going to get H 2 times, I 2 times, J 2 times, and K 2 times. How many times do we get C? C is there. It's occurring twice. It's occurring twice. And what about, okay, we've said L is not appearing. What about A? A is appearing once, twice, 3 times, 4 times, 5 times. So maybe I could write it like this. I could write it as 5 times the multiset consisting of A, so allowing ourselves some sort of linear structure on multisets. This just means the multiset that you get by putting 5 A multisets together. And what else? Well, there's this inner multiset, which are sort of the neighbors of A. I might write that, since it's a factor of 2, 2 times C1 of A. Okay, so where C1 of A means the direct neighbors of A. It's like this, but I'm being more specific. And we also get the outer ring, which are the things which are of distance 2 from A. So we get 2 of those, 2C2 of A. So let me put it this way, that if we take the multiset that we get by the neighbors of A, then what we end up getting is A 5 times, and the direct neighbors of A each twice, and the direct sort of 2 neighbors of A each twice. Okay, so that's more refined data than just counting the degree at A, saying that it has 5 neighbors. It's more information. And so now we're in a position to ask, is this same thing going to happen if we play the same game not at A, but say from some other point, say D or I or L? Are we going to have that same phenomena? Are we going to get the same kind of pattern with the 5 where we started, 2 of the nearest neighbors, and 2 of the 2 neighbors? Right? If we get that, then that's already a reflection of a deeper symmetry that the graph has, that goes beyond just saying that each vertex is of degree 5. Okay, so actually to make that check, you don't actually have to go through all 12 because, as we've already said, there's some natural symmetry that's sort of evident to us. So one should really check it for, say, one of these vertices, say on the inner ring, say C, and then one of the vertices on the outer ring, say I, and check it also for L. So you might want to do that. Okay, you might want to do that just to practice what we're talking about here and check that it all makes sense, and that in this sense we are already seeing some sort of elevated symmetry that this graph has through what's essentially a kind of like a diffusion process where we're starting at one point and then we're going one step and then we're going one more step. Okay, so let's just officially define C sub I of X, X is a vertex, is the M set of I neighbors of X. And that means those vertices which are distance I from X. And distance means you count the minimal number of edges that you need to traverse to get from the initial edge, X, to whatever vertex you're considering. So if we start with A, this central thing, then there's a couple of multisets that appear here. There's C0 of A, things which are of distance 0 from A. Well, there's only A itself there. So that's in green. There's only one of them. And then there's C1 of A. These are the nearest neighbors, the 1 neighbors, if you like. They're indicated by these blue triangles around the vertices. Okay, that's them. And then the things of distance 2 from A, denoted by the squares. There they are there. And finally, things of distance 3 from A. So you have to go 1, 2, 3 steps to get out to this this outer vertex. That's that one there, and of course it only has one element, that multiset, because there's really only one such outside vertex. Okay, so now having this notation, we can now ramp up what I was talking about this sort of going one step followed by one step. We can ramp this up considerably by asking what happens when we combine steps of different sizes. So this first equation is a reflection of what we've just already wrote down, saying c1 squared equals 5c0 plus 2c1 plus 2c2. And the meaning is that if you start at, say, A, and you take a step size of 1, okay, and then you're on this board here, and then you take another step of size 1, okay, then what are all the possible things that you get by doing that in all possible combinations? So you take all possible steps of size 1 from A, and then from each one of those you take all possible steps of size 1. And we've seen that in terms of the multiset language, we're getting 5 of the guys in the center. We're getting 2 of the immediate neighbors and 2 of the 2 neighbors. So similarly, you could calculate C1 times C2, okay, which could be interpreted as doing the following. First, you look at all the 1 neighbors of A. So we're always starting at A here. Okay, so we're starting at A and we're taking one of the 1 neighbors, so one of the blue triangle things. And then from there, we're looking at the 2 neighbors of that. So sort of drawing a circle of radius 2 around this one now. So what would be the things that would be 2 away from this one? Well, that's one of them. Okay. That one is not different. That's the same as that one. So there's one of those. And what else is there? There's that one, okay, and there's that one. So there's 2 of them on the outside ring. And there's also 2 on the inside ring. There's this one and there's this one, okay. So the 2 neighbors of this thing are this vertex, these 2 vertices, and these 2 vertices. And if you look at all those combinations where we start not just at this one, but also these other 4 and sort of add them together, you're going to see that you get 2 times C1 plus 2 times C2 plus 5 times C3. Remember, we've got C3, this one here, and we're going to get that same C3 from each one of these things. So it's a lot like this one, but just a little bit different. Then you can check that C1 times C3 equals C2. What does that mean? So it means that if you start here and go to any one of the 1 vertices, say that one again, and then you go 3 from that. So where's 3 from that? 1, 2, 3. This is the only one which is 3 from that. That's the far one from that. Well, so that's going to be in C2 with respect to A. So as we vary around the circle of radius 1 from A, this composite will vary around this outer C2 circle. So that's why C1 times C3 equals C2. And similarly, you can check that C2 times C3 equals C1. That C2 squared equals 5C0 plus 2C1 plus 2C2. Actually the same thing as that thing. And that C3 squared equals C0. Now you might ask, what about the other relations? There's a few other ones that I haven't written down, namely the ones that involve C0. Okay, but C0 is like the identity, because if you do C0, you're not going anywhere, so you just stay where you are. So those multiplications are also valid, like C0 times C1 will be C1, but we're not going to write them down. So we get this small but attractive algebraic object. And it turns out that this is what's called in physics sometimes a fusion rule algebra. It has some nice properties. Notably amongst these nice properties are, first of all, that's associative. Okay? If you do a step of size 1, and then you do a step of size 2, and then follow that by a step of size 1, that's the same as if you do a step of size 1, and then follow it by the combination of step 2 and step 1. So associativity is kind of obvious. What's not so obvious, perhaps, is commutativity. This is also commutative. That's why I haven't given the products in the other order. If we did C2 times C1, so started here, then first do a C2, and then do the neighbors of C1, we're going to get the same thing. So that's already another reflection of the symmetry that's sitting here in this graph. And now happily we can check that these relations, this little algebra structure that we're getting, which was all based at the point A, is actually independent of the point A. So this diffusion process, which is sort of captured here in these equations, doesn't depend on where we start. And that's a very strong property of this graph. This is telling us that we have a lot of symmetry here. Okay, so this is the diffusion symmetry sort of replacement of the idea of looking for transformations or automorphisms of the graph, which would preserve the graph structure. It's an alternate point of view that turns out to be really powerful because, well, for one thing, it's commutative. Okay, this is a commutative situation. Now, there's an important variant to the algebra structure that I showed you, which transforms the entire discussion into the world of probability. Okay? And that's obtained by making a change of variables. Basically, what we do is we replace these multisets with averages. In other words, we weight the elements in these multisets so that the total mass of each of the multisets that we're considering is 1. So algebraically what that amounts to is taking these capital C's that we've been talking about and replacing them with small c's. Okay? So the small C0 is the same as the big C0 and the small C3 is the same as the big C3 because both of those multisets only have one object in them. However, C1, little c1 is 1/5 of capital C1 and little c2 is 1/5 of C2. So you could take those equations that I've just shown you involving the capital C's and replace the capitals with the little ones. So for example, you could replace capital C1 with 5 times little c1, etc. And then rewrite the equations in terms of the little c's and you get these equations. Let's have a look at them. So now C1 squared is 1/5 of C0 plus 2/5 of C1 plus 2/5 of C2. And now you can interpret this in terms of a probability. This is now a random walk. Okay? It's a random walk that says that if you start at a given vertex and you choose a vertex at random, which is a nearest neighbor, step 1, okay, from the starting point. And then from there, you choose randomly a vertex of also 1 from that point. Then where you end up has a 1/5 chance of being back where you started. It has a 2/5 chance of being on the circle of radius 1 from the starting point and has a 2/5 chance of being on the circle of radius 2 from the starting point. Now, I'm going to illustrate this actually with a diagram, and I'm going to introduce what probably many of you have already realized, that the graph that I've showed you is actually just the one skeleton, the graph of vertices and edges of an icosahedron. Okay, so what I was showing you before was basically the picture where you're looking at this thing here, and here's the ring of 5 that you see, and then on the opposite side, I sort of have to split that and sort of fan it open so it's sort of on the page. So there's a ring of 5, and then there's so that one there's a ring of 5 here, and then there's another ring of 5 back here, and then there's the final last one over here. So if this is A, then this is C1, and this is C2, and this opposite point here is C3. So from this point of view, here's A, there's C1, there's C2, and there's C3. Okay, so let's look at this thing here. What does this tell us in terms of random walks on the icosahedron? It says that if you start, say, at this vertex here, and do a step of size 1, okay? So that means you're at one of these vertices around here. Let's say you're at that one there. Okay, and then you do a step of size 2. So that means from here, you're looking at the circle of radius 2 from here. So 1, 2. That means that's this circle right over here. Okay, so here's our starting point. So I'm talking about this circle here. Okay, and then you look to say, okay, well, that one and that one are in C1. There's a 2/5 C1, and this one are in C2, and there's one possibility of being in C3. So these are the probabilities of getting to various places by having appropriate random walks of steps 1 and 2. And correspondingly, C1, C3 is C2, C2, C3 equals C1. Those haven't changed. And C2 squared is 1/5 C0 plus 2/5 C1 plus 2/5 C2. And C3 squared equals C0. And so having now done this work, we can now actually address this, this interesting question that we started out about the probability of getting back to the starting point if you do a random walk, nearest neighbor random walk of size 11. So that corresponds to taking C1 and raising it to the 11th power. Okay, you're going to get an expression in terms of C0, C1, C2, C3. And the coefficient of C0 is going to be the required probability. That's the probability of getting back to C0, that's the starting point, after taking a one-step random walk 11 times. So how do you calculate? How can you use this information? So this information is very powerful in order to answer that question, because now it becomes algebra. So for example, suppose we have this expression for C1. We're interested in C1 to the 11. Suppose we square this to get C1 to the 4th. Okay? So everything's associative and commutative. Okay? We can use the distributive law because we're just working with multisets. Okay? So if we square this, we're going to get, the square of this, square of this, square of this, twice the various products. Okay, but all these products, like twice the product of these two, is calculated by looking, well, what's C1, C2? There it is there. So you have to multiply that by 2/5 squared, etc. So you perform the arithmetic using all of these relations to simplify things. So you're going to get C1 to the 4th as a linear expression in C0, C1, C2, and C3. And once you've got that, then you could square it again to get C1 to the 8, and then a few more multiplications. You can get C1 to the 11, and then you can read off the coefficient of C0 in that expression. And lo and behold, you get this interesting number. You get, and you can check this, okay, you can do this. You get 1 over 12 times 1 minus 1 over 5 to the 10. 1 over 5 to the 10, that's a very small number. Almost 0, okay? So this is almost 1. So this number is close to 1/12, which is sort of the thing you would expect, because there are 12 vertices, and by the time you've walked 11 steps, you're pretty well anywhere, pretty well with equal probability, but not quite. All right? The probability is just a little bit less than you might expect. It's a little bit less than 1/12. To get back to where you started if you take a random walk of size exactly 11. And so this is illustrating, especially to a physicist, the power of this little algebra that we've created, okay, to solve a pretty sophisticated problem, which is usually tackled usually with some character theory and knowing something about the group of symmetries of the object. So in a standard group theory course, one studies the icosahedron, and one learns that its group of rotations has exactly 60 elements. Okay, so these are the rigid motions of the icosahedron, and they are rotations of different kinds. So if you take two opposite vertices like this, then there's sort of a five-fold rotational symmetry there. Or you could take two opposite faces like this, okay? And since the faces are triangles, there's a three-fold rotational symmetry there. Or you can take opposite edges like those two there, and there's a two-fold rotation. So if you count all those rotations, there's 60 of them. And this group, this abstract group of rotations is called A5. It's the alternating group on 5 things. It has 60 elements. And it's a famous group because it's the smallest simple group, which is not abelian. Now, strictly speaking, to actually obtain this group with 60 elements is a non-trivial task, because first of all, you have to label all these various rotations. You have to give them names, you have to label the edges and the vertices and the faces, and then you have to sort of label consistently these 60 things. And then strictly speaking, you're sort of obliged to create a multiplication table, because that's really what a group is. A group is really a multiplication table. So you have to create the products. If you combine this rotation with this rotation, which rotation do I get? So there's 60 times 60, that's 3,600 entries in this multiplication table. So doing this would probably take a very long day, at least. That's probably if you're very efficient and organized. So that's a lot of information. And that's part of the problem with, or not problem, but that's one of the aspects of dealing with group theory, is that often when we have rich situations, especially in higher dimensions, the groups involved are actually quite big and they can be quite onerous and hard to get one's head around, and so doing mathematics with it's a little bit challenging, because because you have these big groups. Although this one's not so big. This is the smallest of the simple groups. But when we try to solve a problem like this probabilistic walk problem using standard group theory, it'd be a standard exercise in a group theory course, what invariably is involved is the character table of the group. Okay, so the character table is essentially introduced by Frobenius back in the last part of the 19th century. And so characters are particular functions on the group, which are invariant under conjugacy classes. So they're called class functions. So what this character table is telling you is the various values of the characters of the rows, evaluated on the conjugacy classes. So the alternating group is like a group of permutations of 5 things. So here's sort of cycle notation. But these are even, so they all have to be sort of products of an even number of transpositions. So there's just the identity, and here's a product of 2 transpositions, and then cycle 1, 2, 3, the cycle 1, 2, 3, 4, 5, the cycle 1, 2, 3, 5, 4. And here are the various characters. So there's the character 1, and there's this character here, which is relatively simple, and this one here, which is relatively simple. And then these characters 4 and 5 are a little bit more complicated because they involve some root 5s. Okay, so this will be a standard feature, and many physicists will have learned about character tables like this, because they're an important computational device to answer problems like the one I've just shown you. By the way, you might ask, what's this root 5 here, Norman? Well, I don't have my calculator with me, so I can't tell you exactly what root 5 is, but it's somewhere between 2 and 3, and it's some it's some infinite decimal, which from my perspective, there's some serious problems with the meaning of root 5. So already I look at something like this with some skepticism, okay? Like, what are these things exactly? You're not going to be able to compute these things to infinite precision. So, how do you actually work with this? But nevertheless, you can work approximately, and a lot of problems like the one I just showed you, working approximately is not bad. Okay. So, but how does this compare with the diffusion symmetry point of view? Well, let's look at the hypergroup object. That's the object with the little c's, where the probabilities were involved. So there are really 4 objects, C0, C1, C2, C3, representing these different sort of circles or spheres around a central point. And it turns out that in the world of hypergroups, or equivalently fusion rule algebras, there are also characters, okay, and they have certain definitions, but the definitions are simpler than they are in the group theory case. And the reason is because this is all commutative harmonic analysis. So in some sense, this mimics much more closely what happens with commutative groups, like commutative finite groups, where the harmonic analysis is much simpler, okay? So there's 4 characters, the same number as the number of elements in the hypergroup, and here are the various values. There's the identity character, there's this one here with some 1/5, and then there's 2 other ones with some curious number r sub 5. What is that? So there's actually minus 1 over r sub 5 here, 1 over r sub 5 here, and then opposite 1 over r sub 5, minus 1 over r sub 5. Well, r sub 5 is an element of a quadratic extension of the rational numbers. Okay, so this is my way of talking about root 5. I don't want to talk about root 5 as a real number. I want to talk about root 5 as being an element in a particular quadratic extension that we have to build from the rational numbers. Okay, and typically you can think about these as matrices. So if you watch my videos on dihedrons, so I talk about how to deal with complex numbers sort of from a quadratic extension point of view. So it's the same kind of thing. So you have to, but it's an algebraic operation in order to get at this r sub 5, and its crucial property is that r sub 5 squared is 5. And so this is then some kind of analog of that A5 character table that I showed you, but it's simpler. Okay, and it basically addresses the same issue of random walk on the icosahedron. So if you wanted to calculate the probability of getting back to the origin if the walk had, say, 10,000 steps instead of, or maybe say 11,000 steps instead of 11, then you don't want to do it algebraically. Then it's much cleaner to use this character table. There's a very clever and beautiful way of using the character table to make some computations. And the beautiful aspects that the group character tables have are also shared by these ones here. So, and there's a beautiful connection with these things. So we can really see that, I hope you can see that there's at least this possibility that this diffusion symmetry approach, okay, ends up elevating these objects, which we have many different names, including hypergroups and fusion rule algebras, but many of these other names as well, and sort of elevating them to a position where they're of comparable importance to groups and provide important alternatives to making calculations, and also to sort of theoretically understand what's really going on with some aspects of mathematics and physics. So I want to thank you all for listening. I do hope that you'll keep on watching this series and perhaps also think about becoming a member of my Wild Egg Maths channel and watching some of the interesting things that are going on there. And I wanted to also take the opportunity of thanking some of my long-term Patreon supporters who I really appreciate, and I don't often say this, but I do want to occasionally say thank you. So I want to say thank you to Vincent, and to Mark, and to Michael, and to John, Dan, William, and Carrie. Particular generous and supportive people. So in my position, it's great to have some support because I'm kind of taking roads less traveled, and having some people behind me is much valued. So I thank you very much for that. I'm J Wildberger. Thanks for listening.